What in the universe can explode with such power that in a single blink it releases more energy than the sun across its entire lifetime? And why do these signals sometimes appear in places completely empty, with no stars, no matter, and no trace of any cosmic explosion? Gamma rays, the most violent light ever observed, are sending humanity questions that modern science still cannot answer. And the journey to decode them has only just begun. What kind of explosion in the universe is so powerful that in a single heartbeat it can outshine an entire galaxy? And what kind of invisible light could carry that violence across billions of years to quietly flicker in the detectors of a small planet like Earth? When we follow the trail of gamma rays, we are following the signatures of the most extreme moments that reality allows. They are the afterglow of stars dying in fire, of neutron stars colliding in a final embrace, of newborn black holes carving their presence into the fabric of space-time. At its core, a gamma ray is simply light with extraordinarily high energy. If ordinary starlight is like the gentle glow of a candle in a quiet room, gamma rays are like sparks from a cosmic welding torch. They vibrate at such high frequencies that each photon carries a punch strong enough to disturb atomic nuclei. On Earth, we can create gamma rays in nuclear reactors or particle accelerators, but only in small, controlled amounts. Out in the universe, nature produces them in quantities that make all our machines look like toys. To understand where gamma rays come from, imagine a massive star reaching the end of its life. For millions of years, it has fused lighter elements into heavier ones in its core. Eventually, the core fills with iron, an element that cannot release more energy through fusion. The engine stalls. Gravity wins. In a fraction of a second, the core collapses inward. The outer layers crash down, then rebound in a titanic explosion we call a supernova. In some of these deaths, narrow jets of matter are launched at speeds close to that of light, drilling through the star and bursting into space. Within these jets, particles collide violently and produce a storm of gamma rays that can be seen across the observable universe. One way to picture it is to imagine an entire city's worth of lights suddenly focusing into the beam of a single lighthouse. Instead of shining in all directions, the energy is funneled into a thin jet, and if that jet happens to point almost exactly at Earth, we see a gamma ray burst so bright that for a brief moment it outshines every other source in the sky. For a typical gamma ray burst, that moment may last less than 2 seconds. Yet in that instant, the source can emit as much energy as our sun will release in its entire lifetime. Another birthplace of gamma rays lies in collisions of neutron stars. Neutron stars are the crushed hearts of massive suns. City-sized spheres with masses greater than our sun packed into a ball only a few tens of kilometers across. When two of these remnants orbit each other, they slowly lose energy through gravitational waves and spiral inward. In the final moments, tidal forces tear them apart. Magnetic fields twist into knots, and a newborn black hole may form at the center. Once again, powerful jets erupt, and gamma rays stream out across space. A simple analogy here is to imagine two spinning tops made of pure steel colliding on a glass table. Except instead of metal shavings and sparks, the universe produces new elements like gold and platinum, along with a flash of gamma rays that could light up half the cosmos for an instant. The wedding ring on a human hand may carry atoms that were forged in exactly such a collision. accompanied by a scream of gamma light that raced outward long before Earth was born. Gamma rays also emerge from the environments around black holes. When matter falls toward a black hole, it does not simply disappear. It forms a swirling accretion disk, where gas is heated to temperatures so high that atoms are stripped into plasma. Magnetic fields thread this disk, and in some cases they can channel material into jets launched perpendicular to the disk at relativistic speeds. These jets become natural particle accelerators on a scale that dwarfs any human experiment. Electrons and other charged particles spiral along magnetic field lines, and as they do so, they radiate energy in the form of X-rays and gamma rays. An everyday comparison might be a roller coaster designed for particles instead of people. In a laboratory, we build circular tracks and push particles to high speeds using electric fields. Near a black hole, gravity and magnetism provide the track and the power, launching particles to energies we can barely imagine. The gamma rays we observe from active galactic nuclei are the glowing footprints of this invisible roller coaster. The environments that produce gamma rays are so extreme that they stretch our theories of physics. Temperatures can soar to billions of degrees. Densities can rise above those inside atomic nuclei. Magnetic fields can become so strong that they quantize the very vacuum of space. In laboratories on Earth, we can simulate fragments of these conditions for tiny fractions of a second, but never all at once. That is why gamma rays are precious to astrophysicists. They act as messengers from regimes of nature that we cannot reproduce directly. From a scientific point of view, this is both exciting and unsettling. Exciting, because every burst of gamma rays is an invitation to learn about matter and energy at their limits. Unsettling, because sometimes the data do not fit neatly into our models. There are gamma ray bursts that last far longer than theory predicts. Bursts that seem to come from regions with no obvious host galaxy, or signals whose energy distribution refuses to match standard scenarios. Each anomaly is a quiet reminder that our understanding of extreme physics is still incomplete. For people who do not work with equations every day, an easier way to feel this is to think of gamma rays as the universe raising new questions in the most dramatic way possible. A star collapses or two neutron stars collide, and for a brief moment, the cosmos shouts in gamma light. We detect that shout as a pattern in our instruments, then spend years or decades trying to decode what it meant. In that sense, gamma rays are less like answers and more like puzzles. They illuminate, but they also challenge. There is also a more personal lesson in the origin of gamma rays. At first glance, these events seem impossibly distant from everyday human life. They happen billions of light years away, on scales that dwarf not only planets, but entire galaxies. Yet the heavy elements in our bodies, the atoms in our blood, even some of the metals in our technology, were likely created or dispersed by exactly these kinds of cataclysmic explosions. Without supernovae and kilonovae driven to such extremes that they emit gamma rays, the universe would be a much simpler place, mostly hydrogen and helium. Complex chemistry, and with it biology and consciousness, might never have emerged. From this perspective, the terrifying violence of gamma-ray sources begins to look different. They are not just cosmic disasters. They are also creative moments. Stars die so that heavier elements can be scattered into space, later to condense into new stars, planets, and eventually living beings capable of asking where they came from. The same gamma rays that remind us how small and fragile we are also tell us that our existence is tied to the most powerful processes in the universe. If there is a lesson I draw as a scientist, it is that understanding often grows from the edges of what makes us uncomfortable. Gamma rays come from places where our intuition fails, where gravity crushes matter into forms we cannot touch, where magnetic fields twist space in ways we struggle to visualize. Yet by carefully measuring these signals, comparing them with theory, and remaining honest about the gaps in our knowledge, we gradually turn awe into insight. We do not tame the universe, but we learn to read it a little better. In a more meditative sense, gamma rays encourage humility. A gamma ray burst that appears in our detectors tonight may have left its source before our planet even existed. For all the drama of human history, we are newcomers to a cosmos that has been staging these extreme events for eons. When we look up at the night sky, everything seems calm. But hidden within that calm, in wavelengths our eyes cannot see, are reminders that somewhere out there, stars are dying in light so fierce it bends our theories. Perhaps that is the quiet wisdom carried by gamma rays. That creation and destruction are intertwined, that the universe is at once serene and violent, and that even in the most extreme bursts of energy there is information waiting to be understood. We stand on a small world, holding delicate instruments, listening for the faint echo of explosions unimaginably far away. And in those echoes, hidden in streams of gamma light, we find both the story of how matter becomes complex and a reminder of how much we still have left to learn. What if the universe made its first great fireworks show far sooner than it was supposed to? What if, when we look back to a time only 500 million years after the Big Bang, we already see the most violent kind of light that nature can create blazing across young space? Gamma ray bursts that should not yet exist according to our textbooks. That simple question is the beginning of a quiet shock in modern cosmology, and it is the place where the James Webb Space Telescope has started to make even veteran scientists feel strangely unsure. For a long time, the story sounded simple. First, the universe expands and cools. Then, after a few 100 million years, clouds of hydrogen gather, the first stars ignite, and only after they live, evolve, and die can they produce the catastrophic explosions needed to launch gamma-ray bursts. In this picture, there is an orderly queue. First dark ages, then first light, then heavy stars, then their deaths. But when JWST began to look deeper into the cosmic past than any telescope before, it found hints of gamma-ray bursts appearing much earlier than expected, almost as soon as the curtain of the early universe lifted. To feel how strange this is, imagine you are watching a city being built in extreme fast-forward. At the start, there is only empty land. You expect to see surveyors, then foundations, then the steel skeletons of buildings. Only much later, when the city is crowded and old, do you expect to see the occasional building collapse? Gamma-ray bursts in the early universe are like seeing skyscrapers already collapsing in a city where, according to your plans, the first bricks have only just been laid. Something in the timeline no longer fits. Gamma-ray bursts, or GRBs, are not gentle events. They are narrow beams of extremely energetic light, often created when a very massive star collapses into a black hole or when two neutron stars slam together and merge. For a few heartbeats, a single burst can outshine entire galaxies. On Earth, if such a burst happened in our galactic neighborhood and aimed directly at us, it could strip parts of the atmosphere and change the conditions for life. Out in the distant universe, these flashes are signposts, telling us that somewhere, far away and long ago, a star died in a particularly dramatic way. When JWST and other observatories trace these bursts back to their host galaxies and measure how much the universe has expanded since the light left, they sometimes find redshifts that correspond to extremely early epochs. 500 million years after the Big Bang is early enough that many models say there should not yet have been time to build enough heavy stars. Let them evolve, and have them die in collapses powerful enough to launch bright GRBs. Yet the signals are there, brief but undeniable. The question grows sharper. Did the first stars form faster and more efficiently than we thought? Or is there a piece missing from our picture of how these explosions work? One possibility that researchers discuss is that the first generation of stars was very different from the ones we see today. In theory, the earliest stars could have been far more massive, made almost entirely of hydrogen and helium, burning hotter and living shorter lives. If many of them collapsed quickly, they might have produced gamma-ray bursts far sooner than our simple timelines assume. In that case, the puzzle is not that the bursts exist, but that we underestimated how extreme the first stars truly were. Another possibility is more unsettling. Perhaps some GRBs are not coming from the processes we usually imagine. Maybe there are exotic channels that can make ultra-energetic jets without requiring a long chain of star formation and chemical enrichment. Some ideas reach into speculative territory, linking gamma rays to the decay of unusual particles or to processes in dense, early structures that we have not yet properly modeled. These are not settled theories, but their very existence shows how much room there still is for new physics in the deep past of the cosmos. To make this more tangible, think of baking bread. If you mix flour, water, and yeast, you expect to wait for the dough to rise before you see the loaf swell in the oven. If, for some reason, you opened the oven almost immediately and already found fully risen loaves inside, you would have to question either your recipe or your understanding of time. Early gamma-ray bursts are like those impossible loaves. Either the cosmic recipe for star formation is different from what we thought, or the clock we are using to time the process is missing an important step. There is also a very human layer to this story. For decades, cosmology has grown into a precise science. We speak of the age of the universe with decimals. We map its contents into neat percentages of dark matter, dark energy, and ordinary atoms. It is tempting to feel that the broad outline is complete, and that only fine details remain to be filled in. Then, a telescope like JWST quietly reveals objects and events that should not be so mature, so massive, or so violent at such young ages. It is as if the universe gently reminds us that our confidence should always be balanced with humility. From my own perspective, one of the most valuable aspects of these early GRB discoveries is the way they reopen questions that many assumed were already nearly closed. When models work too well, human beings tend to relax. We stop looking for cracks. Anomalies like these bursts force us to look again, to check each assumption. How quickly can gas collapse? How massive were the first stars? How did radiation, turbulence, and dark matter shape the first galaxies? In this sense, the discomfort that scientists feel is not a flaw in the process but a feature. It is a signal that we are once again standing at the edge of what we know. There are lessons here that reach beyond astrophysics. We often build mental models of our own lives that feel as solid as cosmological theories. We say that certain achievements must come only after certain stages, that growth must follow a fixed sequence, that some events are too early or too late to make sense. Yet the universe is showing us that sometimes, under the right conditions, complexity can appear sooner than expected. Structures can form more quickly. Fireworks can begin before the schedule says they should. Perhaps there is a quiet wisdom in letting go of the idea that everything important must arrive on a fixed cosmic timetable. At the same time, there is another lesson that pulls in the opposite direction. We should not throw away our theories lightly. The models that predict slower star formation were built from real data and careful reasoning. When new observations conflict with them, the task is not to abandon structure altogether, but to refine it. In life and in science, a single surprising event does not mean that everything we believed was wrong. It means the picture was incomplete. The challenge is to enlarge the frame without losing what was already understood. As more gamma-ray bursts are detected at high redshift, astronomers will slowly build a statistical map of how often such explosions occurred at different times in cosmic history. With patience, patterns may emerge. We may find that the early universe really did form stars with unusual speed, or that only a few rare regions were extreme enough to produce those first violent jets. Or we may discover hints of something stranger, a new kind of engine powering some of these bursts that will force us to rethink the relationship between gravity, matter, and energy under extreme conditions. In the meantime, there is a certain beauty in not knowing. The afterglow of a distant GRB is a fading fingerprint, a ghost of an event that happened billions of years before Earth existed. When we interpret that faint light with our instruments, we are doing something profoundly delicate, trying to reconstruct the death of a star in a young galaxy, when our own galaxy was not yet born. The fact that these clues do not fit neatly into our present theories is a reminder of how fresh our understanding still is. We are like early cartographers, drawing coastlines from a few scattered landings, occasionally discovering that what we thought was a bay is actually the mouth of a great river. If there is a final thought to carry from these puzzling early gamma-ray bursts, it might be this: the universe is under no obligation to match our expectations. Our equations are tools, not laws written into the fabric of reality. When new observations arrive that disrupt the clean lines of our diagrams, they are not insults to our intelligence, but invitations. Each inconvenient burst of gamma light, roaring out of a universe that was supposed to be too young for such drama, is an invitation to deepen our curiosity, to adjust our models, and to remember that we are still at the beginning of understanding how everything came to be. In that sense, the discomfort these discoveries cause is a kind of gift. It keeps science alive, not as a finished monument, but as an ongoing conversation between the mind and the cosmos. Somewhere, in those first 500 million years, Stars were already being born, living brief and furious lives, and dying in bursts so powerful that their light is only now reaching our telescopes. They did not wait for our theories to be ready. They simply were. And we, arriving late, are left to read the fading signatures of their existence and to let them reshape the stories we tell about the origin and growth of the universe itself. What if the brightest explosions in the universe were being born in places where nothing seems to exist at all? What if the cosmos itself were whispering in the darkness through flashes so powerful that in a single heartbeat they outshine entire galaxies? For decades, written out fully in words, astronomers believed they understood the environments capable of producing gamma rays, those fierce needles of light that carry the highest energies ever observed. They expected them to erupt from crowded stellar nurseries, from collapsing giants, from neutron stars spiraling into one another in a cosmic dance of death. Yet again and again the universe quietly contradicts us. Our telescopes sweep across the sky, and in places that appear utterly empty, void of stars, void of gas, void of any visible structure, a sudden pulse of gamma light appears as if from nowhere. It is as though a match were being struck in a cavern whose walls you cannot see, lighting up an absence we assumed was silence. The mystery deepens because these signals do not merely glimmer, they roar. A single gamma burst can unleash more energy than the sun would emit across its entire lifetime. Yet when we examine the region in all wavelengths, we find no dying star, no explosive remnant, no galactic cradle bustling with creation and collapse. It is like walking through an empty field and suddenly hearing a thunderclap with no storm above. This contradiction pulls at the threads of our understanding, inviting us to step beyond what is familiar and into the subtle terrain where the universe reminds us how little we truly know. I often think of a simple metaphor when explaining this puzzle to my students. Imagine gazing at a vast city at night from an airplane window. The bright districts are the galaxies, the glowing neighborhoods are the stellar clusters, and the dim alleys between them are the cosmic voids. If someone told you that the largest fireworks display ever recorded erupted not from the crowded city center, but from a silent stretch of unlit desert miles away, you would pause. Not because it is impossible, but because it challenges your sense of where great events ought to happen. Gamma rays from empty space force scientists into that same moment of pause. As observations accumulate, a gentle pattern emerges. The universe is not empty, even where it appears so. Space that seems silent may hold ancient dwarf galaxies too faint for our eyes, or compact stellar corpses drifting without companions, or magnetic fields twisted over millions of years waiting for a spark. Some researchers propose exotic possibilities, primordial black holes left from the earliest instants after the Big Bang, or even the annihilation of dark matter particles whose nature remains elusive. Though evidence is still thin, these ideas remind us that unseen engines may lie beneath the surface of the cosmic sea. As I read through the data, what moves me most is not merely the physical mystery, but the emotional one. There is a humility in witnessing nature behave in ways that exceed the rules we once carved into stone, a quiet insistence that discovery begins where certainty ends. When scientists try to trace a gamma flash back to a point in the sky, only to find nothing is less than 0.5 hash is greater than, they are forced into a rare and beautiful state of mind. Curiosity without anchor. It is a reminder that the universe does not owe us explanations. and yet it continues to offer questions that nourish our desire to understand. Examples from recent years illustrate this wonder without requiring technical detail. In one case, a powerful gamma burst was detected in a region so empty that even the deepest infrared surveys saw nothing. No star cluster, no remnant, only darkness. Yet the burst itself carried the unmistakable signature of a massive cosmic event, something that must have involved matter collapsing in extreme gravitational tension. In another example, a persistent glow of gamma light extended across a stretch of intergalactic space where no galaxy was present at all, leading some astronomers to wonder whether wandering black holes might be feeding invisibly on hydrogen too sparse to reveal them. These possibilities do not confuse us so much as they invite us into a deeper kind of listening. As the decades written out fully in words pass, technology sharpens our vision, but the mysteries grow alongside it. The clearer our instruments become, the more the universe reveals that clarity and completeness are not the same. Even when we illuminate the sky in gamma light, the brightest discoveries emerge from the darkest corners, like constellations drawn not with stars but with questions. And in these questions I find a personal truth, that science is not merely the accumulation of answers but the cultivation of wonder. When I reflect on these empty regions where gamma rays bloom, I feel an unexpected sense of peace. They remind me that absence does not imply insignificance. That stillness can conceal extraordinary possibility. Much like human experience, the quietest places often hold the most transformative events. A life may appear empty from the outside, yet inside it may contain collisions, rebirths, collapses, and revelations invisible to others. The universe mirrors us in this way, its silent expanses filled with unseen power. And so the lesson I draw from gamma rays emerging out of nothingness is simple and profound. Never assume that what you cannot see has no story. Never imagine that darkness is lifeless. The cosmos teaches us gently that the greatest forces may be at work where our eyes find only emptiness. That meaning can reside in places we overlook. And that discovery begins the moment we admit how little we truly perceive. Gamma rays from the void are not merely scientific puzzles. They are meditations on the nature of existence itself, constant reminders that the universe does not reveal everything at once. It unveils its secrets in flashes, brief but brilliant, like thoughts from a mind far older than ours. And each flash invites us to listen, to wonder, and to continue searching with patience and awe. What would you think if the most violent flash of light in the universe decided to stop behaving like a flash and instead refused to fade for almost half an hour? For many years, astronomers believed gamma-ray bursts were cosmic sprints, short explosions that dump unimaginable energy into space in a few seconds and then vanish. The physics seemed clear enough. Collisions of neutron stars, or the core collapse of a massive star switch on a narrow jet of gamma rays for a brief moment. Then the engine chokes off. Yet in recent observations we have seen something that does not fit this tidy picture at all. Bursts that do not end when they are supposed to end. Gamma ray beacons that burn on for hundreds or even thousands of seconds, as if some hidden engine in the dark is refusing to stop. To feel how strange this is, imagine you are watching a storm from far away. You see a lightning bolt, a blinding spike of light that lasts for a heartbeat and disappears. That is what normal gamma-ray bursts are like on a cosmic scale. Now, imagine a lightning bolt that stays on the sky for 20 minutes. not flickering, not repeating, but one continuous blaze etched across the clouds. At some point you would stop calling it lightning and start asking whether the thing you are seeing follows a different rule entirely. This is exactly the feeling many scientists describe when faced with so-called ultra-long gamma-ray bursts. Events that keep pouring out high-energy photons long after every standard model says the engine should be dead. In the classic picture, a short burst lasting less than 2 seconds is often linked with the merger of two neutron stars. Compact remnants spiraling together until they collide and briefly create a jet of gamma rays. The longer bursts, those lasting a few seconds to a couple of minutes, are usually tied to the collapse of a very massive star that forms a black hole and punches a jet through the dying star before everything falls silent again. Both kinds share one assumption. The central engine works for a short time, then runs out of fuel or collapses into a quiet state. But when we detect a burst that simply keeps going for 1,000 seconds or more, the timescale no longer matches any of these engines. It is like watching a candle where you expected a camera flash. One way to picture the problem is to think of a hose spraying water. In the usual bursts, someone opens the tap for a second or two. The jet sprays violently. Then the tap slams shut. In an ultra-long burst, the tap seems to stay open for an entire episode of your favorite show, and the flow hardly weakens. For the jet to remain collimated and powerful for that long, the object driving it must stay organized in a way our current simulations struggle to explain. We can write equations for accretion disks feeding black holes, for magnetic fields twisting and launching outflows. But keeping everything stable on these timescales is far from trivial. Some researchers have suggested that these long-lived bursts might come from the collapse of especially large and extended stars, giant envelopes of gas that take more time for the jet to bore through. In this picture, the jet does last longer simply because it has more material to plow through before it can escape into space. Others prefer a different idea, that the core of the dying star does not become a silent black hole immediately, but instead forms a highly magnetized neutron star called a magnetar, spinning rapidly and losing energy over many hundreds of seconds. The magnetar acts almost like a cosmic dynamo, gradually feeding power into the jet until it finally slows down. Each scenario has strengths and problems. Neither fully explains every observed detail. The tension between data and theory shows up in small things too, in the way the brightness of the burst declines, in the color of the afterglow, in the host galaxies where these events occur. When you line up the observations, some features look like familiar long bursts. Others resemble something new. It is as if nature is blending multiple engines in ways that resist our neat categories. For a scientist, this mixture is both frustrating and beautiful. Frustrating because our models were supposed to be general. Beautiful because the universe is reminding us that our categories are human inventions, not laws carved into the fabric of reality. To make this more intuitive, think of a concert hall. The standard bursts are like short drum hits, sharp and percussive, easy to analyze. You can say this is a snare, that is a kick drum. Ultra-long bursts are like a strange instrument that keeps ringing and changing tone while you listen, at times sounding like a drum, at times like a bowed string, sometimes fading, sometimes surging again. If you only knew how to analyze short hits, this evolving sound would confuse you deeply. You would either have to invent a new instrument or admit that your language for music was incomplete. tia gamma keo dai kung vei. Chung ip chung ta fai mer, rong von, tu vung vot li kwa min. There is also a quiet human dimension to this story. Many of the astronomers who work on gamma-ray bursts have spent entire careers chasing these events. From the first detections by military satellites looking for nuclear tests, to fleets of modern observatories ready to swivel in, seconds when an alert arrives. They built a narrative in which bursts seemed at least broadly understood. One class for mergers. One class for collapsing stars. Then the universe placed these long-lived signals on the table like a riddle, as if saying your story is good, but it is not finished. For a thoughtful scientist, Boy Roy is not a failure. It is a sign that you have reached the frontier where real discovery begins. On long nights when data from a fresh burst scrolls slowly onto the screen, it is easy to imagine the scene at a different scale. Somewhere in a distant galaxy, a massive star has spent millions of years quietly fusing elements in its core. It dies in seconds, tearing itself apart, forming a black hole or a newborn magnetar, launching jets that tunnel through its own body and out into space. Those jets cross the void for billions of years, slipping between galaxies, scattered by nothing, until a tiny detector on a small world around a modest star happens to be pointed the right way. For a moment, we are aligned with an event that has nothing to do with us, and yet its light writes itself into our instruments. The fact that some of these messages last longer than we expected is less a violation of nature and more a clue that the drama inside these dying stars is richer than our early sketches. From my perspective as someone who cares about both science and the stories we tell about it, these puzzling gamma-ray bursts carry at least two quiet lessons. The first is intellectual humility. Whenever we say we have understood something completely, the universe finds a way to show us a corner that does not fit. Ultra-long bursts are that corner in high-energy astrophysics. A reminder that even in fields packed with equations and simulations, reality still has room to surprise. The second lesson is about patience. Both the bursts and our effort to decode them unfold on long timescales. A gamma-ray jet can blaze for thousands of seconds. Its light then travels billions of years. Our detectors watch for a few hours. Our theories evolve over decades, spelled out as the 1970s, the 1990s, the 2020s. In that chain, our personal lifetime is just another short flare. Yet within that flare we have the chance to notice, to question, and to refine our understanding. Perhaps the most moving thought is that these events are not rare at the scale of the cosmos. Stars are dying in distant galaxies right now. Jets are piercing through stellar envelopes, some of them short, some drawn out into mysterious long performances. Most will never be seen by us. Their light will miss our tiny planet entirely. The few that do reach us become precious, not because they were meant for us, but because we happen to evolve eyes and instruments capable of noticing them. When we study a gamma-ray burst that refuses to fade on schedule, we are not correcting a small technical error in a theory. We are listening more carefully to a universe that has been telling its own story long before humans appeared. These stubbornly long signals are like verses that do not fit the rhythm we expected, forcing us to rewrite the song rather than force the note into the wrong bar. In the end, the puzzle of gamma rays that last too long is less about one specific mechanism and more about our relationship with the unknown. We point our telescopes at the sky. We build models with the best tools we have. and then we let the data argue back. When a burst runs on for 1,000 seconds, it is the universe gently saying you have more to learn. If we can meet that message not with disappointment but with curiosity, if we can accept Boy Roy as an invitation rather than an embarrassment, then each new puzzling gamma-ray burst becomes a quiet teacher, reminding us that in this vast and ancient cosmos, the most powerful light is not only what blinds our detectors, it is also what keeps our minds open. What does it truly mean when a beam of invisible light born in a distant galaxy travels across billions of years of cosmic silence, only to reach Earth with enough power to shake the upper atmosphere and overwhelm instruments designed for the most violent events in the universe? When astronomers observed GRB 221009a, they realized they were witnessing something that did not simply challenge human understanding but gently and relentlessly pushed against the limits of what we thought possible. A single burst of gamma radiation traveled farther than imagination can stretch. Yet when it arrived, it lit the ionosphere with subtle disturbance. Silenced sensors that had survived storms of earlier decades, spelled as the 1980s and the 1990s, and quietly rewrote the scale by which cosmic brilliance is measured. To sense the magnitude of such an event, imagine a simple flashlight in a quiet night field. Its beam stretches outward, thinning, softening, losing strength with every meter until it lands on a distant friend as nothing more than a pale glow. Now replace the field with a gulf so wide that even light needs billions of years to cross it. Replace the flashlight with the most energetic radiation known to nature, and imagine that after all that distance, the beam still strikes your world with enough intensity to alter the sky itself. This is the quiet paradox that unsettles scientists. The idea that something can fade across unimaginable scales, and yet arrive with undiminished power. Gamma rays arise in places where matter and gravity reach their breaking points, forged in collapsing giant stars whose final breaths become cosmic jets, in the collision of neutron stars where densities defy intuition, and in the swirling accretion around black holes where space-time curves like a trembling ribbon. These environments focus energy into narrow beams, accidents of geometry that sweep across the galaxy like silent cosmic lighthouses. Most never touch our planet. Yet once, in a long cosmic while, Earth happens to drift into the thin path of one. GRB 221009a was such a moment. The light that reached Earth began its journey before the first forests rose, before the early ancestors of humankind even stood upright. Across the deep corridors of time, the burst retained an intensity that startled every detector that caught its arrival. Scientists described it as the brightest of all time, not out of poetic exaggeration but because nothing recorded in the age of satellites from the 1970s to the 2020s had ever carried such strength. The universe seemed to whisper and roar at once, showing us what extremes lie beyond the borders of our familiar skies. Even more astonishing is the durability of these beams, a stream of photons holding their shape across billions of years, as if distance itself were irrelevant, suggesting that cosmic jets are more stable, more focused, and more resilient than earlier models predicted. This persistence forces scientists to revisit assumptions about how matter collapses, how magnetic fields constrain energy, and how jets maintain coherence across cosmic voids that stretch beyond our intuitive sense of scale. A simple analogy reveals part of the mystery. Picture a strong ocean wave traveling across an entire planet, its edges dispersing, its energy thinning, its shape changing with every shoreline it meets. A gamma-ray burst is nothing like that. Instead, it behaves like a perfect crest that refuses to break, carrying its identity unchanged across cosmic distances so vast the human mind can barely hold them. As these beams reach us, they remind our species how delicate our position in the universe truly is. Earth sits quietly in a small spiral arm of the Milky Way, unaware of the cosmic storms that sweep far beyond our neighborhood. A single alignment, a jet pointed at our world, can rewrite atmospheric chemistry, disrupt communications, and reshape our understanding of cosmic risk. Yet amidst this fragility lies a deeper lesson, one that transcends fear and leans toward curiosity. These bursts teach us that the universe is not merely a place of destruction, it is also a place of profound coherence, where events across billions of years can converge with extraordinary precision onto a tiny world that listens. They urge us to keep watching, to keep building instruments that sharpen our senses to the cosmic whisper, and to remember that every gamma-ray burst is both a warning and a gift. A reminder of the universe's immensity and a demonstration of humanity's growing ability to understand it. From my own perspective, GRB 221009 A is more than a scientific event. It is a humbling cosmic gesture, a quiet invitation to expand the horizon of what we believe possible. For in its arrival, I see not only the universe's power, but also our species' resilience and longing to comprehend. The burst traveled across eras before our ancestors learned fire, across epochs before our languages formed, across the long river of time until it met eyes capable of wonder. And the lesson it leaves is gentle but enduring, that even the most extraordinary forces of the universe can become teachers, that fragility can coexist with meaning, and that humanity's curiosity is itself a form of light. The universe is vast, but our attention to it, our disciplined desire to understand, becomes a bridge across that immensity. Gamma rays may travel billions of years to reach us, but in the moment we observe them, the cosmos feels just a little closer. Have you ever wondered what truly happens when a messenger of impossible energy, born in the most violent corners of the universe, reaches the quiet blue shell of our world's atmosphere? What does a beam of light so powerful it could unravel atoms do when it finally touches Earth? And why are scientists able to study something that never actually reaches the ground? This question hides a story as delicate as mist and as fierce as a supernova. A story where the sky itself becomes both a shield and a cosmic canvas. Gamma rays arrive from places where nature bends the limits of imagination. From stars collapsing into black holes. From neutron stars spiraling into each other in violent dances that shake space-time. From ancient explosions that lit the early universe long before the 1990s. These rays carry with them the memory of destruction and creation. And yet, when they reach Earth, they do not burn the oceans or carve scars into the continents. Instead, they whisper their presence through the sky itself. When a gamma photon strikes the upper atmosphere, it meets molecules of nitrogen and oxygen drifting in their gentle patterns. But the collision is not gentle at all. The energy of the photon is so immense that the atmosphere cannot simply absorb it. So instead, the universe performs a transformation that is both violent and elegant. The photon gives birth to what scientists call an air shower, a cascade of new particles fanning out like the petals of an invisible cosmic flower. Electrons burst forward. Positrons shimmer into existence beside them. Muons streak downward at near light speed as if they have somewhere urgent to be. In that single moment, the sky becomes a chamber of creation, turning one impossible photon into a rain of particles that dances all the way toward Earth's surface. And yet, despite this energetic storm, no human ever feels it, because the atmosphere does its job perfectly. What falls upon the ground is not the original gamma ray, but its echoes, the whispers of its journey, the signatures of particles born in the high, thin air. This is how scientists study something that never reaches the soil. They look not for the arrow, but for the ripples it leaves behind. Imagine a stone dropped into a distant lake that you cannot see. You cannot touch the stone, but you can watch the circles spreading across the water. And from those circles you can understand the stone's size, its speed, its story. That is how ground-based observatories study gamma rays, by reading the circles etched into the sky by a particle they will never directly meet. One example makes this even clearer. Picture a gamma photon traveling for billions of years across the dark between galaxies, perhaps born when two neutron stars collided in a brilliant flare of gravitational waves and fire. When this photon finally reaches Earth, it strikes the atmosphere above the Andes Mountains, triggering an air shower that spreads across hundreds of meters. And the Cherenkov telescopes on the ground see a brief blue flash lasting less than a billionth of a second. From that flash, scientists reconstruct the entire cosmic journey of the photon, and the universe reveals another fragment of its truth. Or imagine a muon, born from a gamma ray high in the stratosphere, racing downward at nearly the speed of light, passing through mountains, walls, bodies, without slowing. A single detector deep underground registers its arrival, and that one faint signal becomes a clue that somewhere above, a gamma photon sacrificed itself to send that muon across the world. These examples show how the universe communicates indirectly, how its greatest energies hide within delicate signatures, how its mysteries reveal themselves not through obvious shouts, but through soft, fleeting impressions. And as we trace those impressions, our understanding grows, and with it our sense of wonder. The poetic irony is that gamma rays are too powerful for us to see directly, yet too subtle for us to ignore. They teach us that even the most violent forces in the cosmos can become gentle teachers when filtered through the atmosphere, turning destruction into information, chaos into knowledge. As I reflect on this, I find that the lesson is larger than physics. Just as the atmosphere transforms danger into insight, our own lives often turn collisions into clarity, difficulties into understanding, uncertainty into illumination. Perhaps this is why studying gamma rays feels both scientific and spiritual, reminding us that what arrives with force can become meaningful if we learn to read its patterns. There is also a humility in this dance between light and air, for gamma rays traveled across time, stretching back before the 1880s, long before Earth knew human voices. Yet their final story unfolds in the thin blue veil around our world, a veil that protects us and teaches us simultaneously. In the end, the interaction between gamma rays and the atmosphere is more than a physical process. It is a conversation across cosmic distances. The universe sends its fiercest messengers, Earth softens their arrival, and humanity learns from the traces they leave behind. And perhaps that is the quiet truth at the heart of this phenomenon, that even the most powerful light in existence must pass through gentleness before becoming knowledge. As gamma rays continue to fall upon our world in silent sprays of electrons, positrons, and muons, They remind us that the cosmos is both violent and tender. That understanding requires patience, and that every message worth receiving arrives transformed in some way. And so we look upward, toward the place where invisible storms unfold, and we listen for the lessons carried in every cascade of particles. Because in that delicate rain of energy, the universe continues its long conversation with us, inviting us to wonder, to question, and to see our small blue world as a participant in something far greater than itself. What if the brightest signals rising from the heart of our galaxy are not coming from stars at all? What if the Milky Way is glowing in a language we still do not understand? When astronomers point their most sensitive instruments toward the galactic center, they do not just see the usual crowd of stars, gas, and dust. They see an extra glow of high-energy gamma rays that should not be there. It is as if the core of our galaxy is whispering in the most energetic light in the universe, and every time we try to translate that whisper, the meaning slips just beyond our reach. Gamma rays are not gentle light. They are photons carrying so much energy that a single one can be millions or billions of times more energetic than the visible light that reaches your eyes right now. We know they are born in violent places where massive stars collapse, where neutron stars collide, or where matter is torn apart near black holes. So, at first glance, it seems simple to explain a bright patch of gamma rays at the center of the Milky Way. That region is crowded and chaotic, filled with old stars, young stars, remnants of ancient explosions, and a supermassive black hole called Sagittarius, a star sitting like a silent anchor at the core. Surely all of that activity should make gamma rays. Yet when scientists add up everything we know, every supernova, every pulsar, every outburst from the central black hole, the numbers still do not match the glow. There is too much gamma light and not enough known engines to power it. To feel how strange this is, you can imagine standing on a hill outside a great city at night. You know how many buildings are there, and how many street lamps and windows are expected to be lit. You build a careful model of the skyline in your mind, and you predict how bright the city should look from a distance. But when you actually look, the city is far brighter than your calculation. You check again. You count the neighborhoods, the towers, the billboards. Still, the excess light remains, as if someone has switched on a hidden layer of lamps that you cannot see directly. That is what the gamma ray excess at the galactic center feels like to astrophysicists. A glow without enough visible sources. At first, many researchers thought that perhaps the counting was simply incomplete. Maybe there are thousands of faint pulsars clustered near the center, each one a spinning neutron star acting like a lighthouse of high-energy radiation. From far away, a swarm of such faint lighthouses could blend into a smooth glow. This idea is attractive because it uses known physics and known objects, and it is always comforting when the universe can be explained without rewriting the rules. But the closer we look, the more subtle the picture becomes. Some analyses of the spatial pattern of gamma rays suggest small clumps that could match hidden pulsars. Other analyses using different techniques suggest the signal is too smooth, too diffuse to come from discrete sources alone. The data begins to resemble a mirage that changes shape whenever we adjust our instruments and our methods. So another possibility steps into the discussion, one that sounds bold even to scientists who are used to dealing with exotic ideas. Perhaps the extra gamma rays are not coming from ordinary matter at all, but from dark matter. In many models, dark matter is made of particles that rarely touch normal atoms, yet can sometimes collide with each other and annihilate, converting their mass into pure energy, including gamma rays. If the center of the galaxy is where dark matter is most densely packed, then it is also where those annihilations would be most common and where the gamma signal would be strongest. Seen through this lens, the galactic center glow could be more than a puzzle. It could be a long-awaited clue to the identity of the invisible mass that shapes galaxies and cosmic structure on the largest scales. To make this less abstract, imagine you are watching people move in a dark room where you cannot see their bodies. You only see flashes of light whenever two people bump into each other. After some time, you notice that the flashes are more frequent near the middle of the room than near the walls. Even without seeing the people directly, you can guess that more of them are crowded near the center. In the same way, if dark matter particles annihilate and emit gamma rays more often where they are densest, then the Milky Way might be telling us about the invisible crowd gathered at its heart through these mysterious flashes. However, the universe rarely offers a clean answer. The dark matter explanation depends on what kind of particle dark matter is, how massive it is, how often it annihilates, and how its density changes with distance from the center of the galaxy. For every set of parameters that fits the gamma-ray excess, another study suggests that astrophysical sources could also fit the data with a different set of assumptions. Like a balance that tips back and forth between two possible truths. The interpretation of the galactic center glow shifts as new observations and new statistical methods appear. This is where the emotional side of science quietly enters, even in a field that prides itself on objectivity. As a scientist, you hope for clarity. You dream of that moment when a line on a graph rises so distinctly that all doubt falls away. With the gamma rays from the galactic center, that moment has not yet come. Instead, we live in a long twilight of almost answers. 1 month, a paper claims strong evidence that the glow is best explained by many unresolved pulsars. Another month, a reanalysis argues that the pattern fits dark matter better than any population of known sources. Each time the community gathers, examines the methods, the assumptions, the hidden biases, and slowly refines the picture without quite closing the case. In that slow process, there is both frustration and a quiet kind of beauty. The universe is refusing to be rushed. If you want a simpler picture, you can think of the Milky Way as a vast living city of stars. Supernovae are like the fireworks of state, stellar death lighting up the neighborhoods where massive stars once lived. Pulsars are like rotating beacons on distant towers. Our central black hole is a heavy governor at City Hall, occasionally flaring when it swallows gas. We know how bright each of these elements should be in gamma rays, and we try to sum them like an accountant balancing an enormous cosmic ledger. When the books do not close, when the measured brightness remains higher than the expected value, it forces us to ask whether there is an entire class of activity in the city that we have never taxed or measured before. Dark matter annihilation would be like discovering an invisible population whose presence is only revealed through the heat they release when they collide. In my own view, the most important part of this story is not which explanation eventually wins, but how we behave while the answer is still unknown. It is tempting to fall in love with one idea, to champion dark matter or hidden pulsars as if they were a team in a game. But the universe is not obligated to match our preferences. The discipline of good science is to hold our favorite theories gently, to test them honestly, and to let them go when the evidence demands. The galactic center gamma glow is a training ground for that discipline. It demands humility because our best models still leave room for surprise, and it demands patience because the instruments that might finally decide the issue are still being planned and built. There is also a softer lesson for anyone listening, even if you never work with gamma-ray data. We often want reality to be simple and quickly explained. Yet, some of the most interesting truths sit in the space where several explanations are possible and none is yet complete. The glow at the heart of the Milky Way reminds us that mystery is not a failure of knowledge, but a stage in its growth. Just as your eyes need darkness to see the faintest stars, our understanding sometimes needs unresolved questions to reveal its own limits and to point the way forward. When you imagine the night sky, it is easy to think of constellations and gentle starlight. But layered beneath that calm picture is a hidden storm of high-energy events. Gamma-ray bursts blinking on in distant galaxies. Jets from black holes drilling through intergalactic space. And this persistent, enigmatic glow rising from the center of our own galaxy. Somewhere in that glow there may be the fingerprints of dark matter, the very substance that shepherds galaxies into their cosmic web. Or perhaps there is a population of strange stars crowded so tightly together that we can only sense their combined breath. Either way, the signal is real, and it is telling us that the core of the Milky Way is more than just a dense cluster of familiar objects. It is a laboratory where gravity, time, and quantum physics meet in ways we are only beginning to trace. So the next time you look up and see the faint hazy band of the Milky Way stretched across the sky, you can remember that at its center, far beyond your sight, there is a glow in gamma light that keeps the finest minds on Earth awake at night. It is a reminder that even in an age of precision astronomy and powerful telescopes, the universe still holds regions where our models tremble and our confidence must give way to curiosity. In that sense, the mysterious gamma rays from the heart of our galaxy are not just a puzzle for experts. They are an invitation for all of us to stay open to what we do not yet understand, to accept that some answers arrive slowly, and to find peace in the long, quiet arc of discovery that unfolds over lifetimes rather than moments. What if somewhere in the universe a single particle of light carried more energy than all the collisions we can create in our most powerful machines on Earth? What kind of engine of nature could launch such a photon across the void? And at what point do our familiar laws of physics begin to tremble in front of it? When astronomers talk about ultra-high energy gamma rays, they are speaking about photons whose energy reaches into the tera-electron-volt and peta-electron-volt range, millions and billions of times more energetic than the light your eyes can see. On Earth, our most advanced accelerators can push protons close to this regime. Yet a single gamma ray arriving from deep space can casually match or surpass what entire rings of magnets and superconducting technology struggle to produce. To me, that contrast is the first shocking lesson. These particles whisper, the universe is not just a little bit stronger than us. It is unimaginably more resourceful. To feel how extreme this is, imagine you hold a grain of sand in your hand. Now picture that grain containing the kinetic energy of a speeding train, not spread over its whole mass, but packed into the motion of a single microscopic speck inside it. Ultra-high energy gamma rays are like that. A ridiculous amount of energy poured into one tiny quantum of light. When they strike Earth's atmosphere, they trigger avalanches of secondary particles that cascade for many kilometers, lighting up detectors, even though the original photon never reaches the ground. Observatories like Hess, MAGIC and the Cherenkov telescope array read these cascades the way a seismologist reads ripples in the crust, trying to reconstruct the distant explosion that sent them here. Yet the great puzzle remains. How does the universe accelerate anything to such madness? In our laboratories, we carefully shape electromagnetic fields. We bend beams. We build colossal rings to give particles a tiny push each turn. Out in space, there is no engineer, no polished metal, only magnetic fields frozen into plasma, shock waves from stellar explosions, and the violent surroundings of black holes and neutron stars. Somehow, these chaotic environments act like natural accelerators, flinging particles to energies that make our finest machines look like toys. One simple picture we often use is that of a cosmic pinball machine. A charged particle like a proton is born near a supernova shock, a place where expanding stellar debris slams into the surrounding gas. Each time it crosses the shock front, it can gain a little energy as if bouncing between two moving mirrors. After many crossings, its energy can grow enormously, until eventually it escapes. When such a particle later collides with gas clouds or starlight, it can produce gamma rays with energies in the tera-electron-volt range. This idea is elegant, but as we push to the most extreme events we see, into the peta-electron-volt regime, it begins to strain. The universe seems to be playing a deeper game than a simple pinball analogy can capture. A second example that helps ground this in something familiar is to compare timescales. In a particle accelerator, the beam remains confined for tiny fractions of a second before colliding. In contrast, a proton spiraling around the magnetic fields near a spinning black hole can keep gaining energy for years, centuries, even longer. The black hole does not switch off at the end of a grand cycle. It keeps dragging space-time itself, whipping nearby plasma into jets that can stretch across entire galaxies. In those jets, we suspect, some particles ride the magnetic structures like surfers on titanic waves, siphoning rotational energy from the black hole and later radiating it back to us as ultra-high energy gamma rays. We do not yet have a complete theory that captures every detail, but the image alone is enough to tilt our sense of scale. What makes these photons so unsettling to modern physics is not only their power, but the fact that they still obey quantum electrodynamics with unnerving precision. We look for cracks in the theory at these energies, tiny deviations from what our equations predict, hints that space and time might have a grainy structure, or that light might propagate differently at different energies. Yet so far, even the most extreme gamma rays behave as if the vacuum were perfectly smooth, as if relativity and quantum theory are still quietly in charge. In a sense, the universe shouts with incredible violence, but the mathematics we built in the early 20th century still listens without flinching. That harmony between wild phenomenon and calm equation is beautiful, and also a little frustrating for anyone hoping to catch nature breaking its own rules. At the same time, these particles act as messengers from otherwise unreachable realms. When a distant galaxy flares in gamma rays, we are seeing processes that happen near its central black hole, in regions we could never visit with a probe. Because gamma rays travel in straight lines and are not easily deflected, they carry a kind of direct line of sight back to their birthplace. In my view, every detection of an ultra-high energy photon is like receiving a postcard from the brink of some cosmic catastrophe, stamped with conditions of density, field strength and motion that no laboratory can recreate. They let us test how matter behaves in magnetic fields billions of times stronger than anything we can produce, how shocks propagate in plasmas stretching over light years, how particles respond when space-time itself is twisted by rotation and gravity. There is also a softer lesson hidden inside this very harsh light, a lesson about scale and humility. When we first built giant colliders, it was tempting to think of them as final steps toward reaching the fundamental energies of nature. Then the sky informed us, gently but firmly, that particles have been reaching far higher energies for billions of years without any human assistance. Above our heads, in a thin film of atmosphere, cosmic rays and gamma rays are constantly performing experiments for free. Our role is not to dominate that process, but to learn how to read it. For a scientist, that recognition can be both humbling and strangely comforting. We are not the authors of the laws we study. We are the readers of a script the universe has been writing since long before the Earth cooled. From a more personal standpoint, I find that ultra-high energy gamma rays challenge not just equations, but also narrative. We like stories where causes and effects are tidy, where a single supernova is responsible for a single burst. Yet the more we learn, the more each observed photon seems to be the product of layer upon layer of history. The star that exploded had to form in a particular pocket of a galaxy, shaped by merger events, by earlier generations of stars, by flows of gas stirred up on scales of millions of light years. By the time one gamma ray arrives at our detectors, it carries the imprint of that entire cosmic genealogy, and our task is to disentangle it with just a few flashes of light. In that sense, studying these rays feels very close to philosophy, even to meditation. You are constantly reminded that every moment of observation rests on an ocean of hidden causes. The practical lesson for everyday life may seem distant at first, yet it is there. Ultra-high energy gamma rays show that nature can store and release enormous power in ways that are not obvious from local conditions. A quiet patch of sky can conceal an engine capable of reshaping its galaxy, just as a seemingly ordinary situation in our own lives can hide deep potential, or deep risk. They teach patience too. These photons might travel for billions of years before meeting a detector we built in a single human lifetime. Our efforts belong to a much longer story, and that awareness can soften the pressure we place on immediate results. In the end, ultra-high energy gamma rays are not just technical curiosities for specialists. They are part of a broader conversation between humanity and the cosmos. We shine radio waves and laser beams into space. We launch probes and we build colliders. The universe replies with jets from black holes, with the afterglow of supernova, with particles that hit our atmosphere carrying energies beyond anything we dared to plan. Each time we catch one of those photons, we are given a chance to refine our theories, to adjust our sense of what is possible, and to remember that the greatest accelerator is not buried underground, but woven into the fabric of space-time itself. And perhaps the quietest, most meditative thought of all is this: somewhere right now, far beyond the edge of our solar system, a single gamma ray is beginning a journey that will outlast civilizations, carrying with it a tiny but precise record of an event we have not yet imagined. Whether we are ready to read that record when it arrives is up to us. What if somewhere in the universe a single particle of light carried more energy than all the collisions we can create in our most powerful machines on Earth? What kind of engine of nature could launch such a photon across the void? And what point do our familiar laws of physics begin to tremble in front of it? When astronomers talk about ultra-high energy gamma rays, they are speaking about photons whose energy reaches into the tera-electron-volt and peta-electron-volt range, millions and billions of times more energetic than the light your eyes can see. On Earth, our most advanced accelerators can push protons close to this regime. Yet a single gamma ray arriving from deep space can casually match or surpass what entire rings of magnets and superconducting technology struggle to produce. To me, that contrast is the first shocking lesson these particles whisper. The universe is not just a little bit stronger than us. It is unimaginably more resourceful. To feel how extreme this is, imagine you hold a grain of sand in your hand. Now picture that grain containing the kinetic energy of a speeding train, not spread over its whole mass, but packed into the motion of a single microscopic speck inside it. Ultra-high energy gamma rays are like that. A ridiculous amount of energy poured into one tiny quantum of light. When they strike Earth's atmosphere, they trigger avalanches of secondary particles that cascade for many kilometers, lighting up detectors even though the original photon never reaches the ground. Observatories like Hess, MAGIC and the Cherenkov telescope array read these cascades the way a seismologist reads ripples in the crust, trying to reconstruct the distant explosion that sent them here. Yet, the great puzzle remains. How does the universe accelerate anything to such madness? In our laboratories, we carefully shape electromagnetic fields. We bend beams. We build colossal rings to give particles a tiny push each turn. Out in space, there is no engineer, no polished metal, only magnetic fields frozen into plasma, shock waves from stellar explosions, and the violent surroundings of black holes and neutron stars. Somehow, these chaotic environments act like natural accelerators, flinging particles to energies that make our finest machines look like toys. One simple picture we often use is that of a cosmic pinball machine. A charged particle like a proton is born near a supernova shock, a place where expanding stellar debris slams into the surrounding gas. Each time it crosses the shock front, it can gain a little energy, as if bouncing between two moving mirrors. After many crossings, its energy can grow enormously, until eventually it escapes. When such a particle later collides with gas clouds or starlight, it can produce gamma rays with energies in the tera-electron-volt range. This idea is elegant, but as we push to the most extreme events we see, into the peta-electron-volt regime, it begins to strain. The universe seems to be playing a deeper game than a simple pinball analogy can capture. A second example that helps ground this in something familiar is to compare timescales. In a particle accelerator, the beam remains confined for tiny fractions of a second before colliding. In contrast, a proton spiraling around the magnetic fields near a spinning black hole can keep gaining energy for years, centuries, even longer. The black hole does not switch off at the end of a Grant cycle. It keeps dragging space-time itself, whipping nearby plasma into jets that can stretch across entire galaxies. In those jets, we suspect, some particles ride the magnetic structures like surfers on titanic waves, siphoning rotational energy from the black hole and later radiating it back to us as ultra-high energy gamma rays. We do not yet have a complete theory that captures every detail, but the image alone is enough to tilt our sense of scale. What makes these photons so unsettling to modern physics is not only their power, but the fact that they still obey quantum electrodynamics with unnerving precision. We look for cracks in the theory at these energies, tiny deviations from what our equations predict, hints that space and time might have a grainy structure, or that light might propagate differently at different energies. Yet so far, even the most extreme gamma rays behave as if the vacuum were perfectly smooth, as if relativity and quantum theory are still quietly in charge. In a sense, the universe shouts with incredible violence, But the mathematics we built in the early 20th century still listens without flinching. That harmony between wild phenomenon and calm equation is beautiful, and also a little frustrating for anyone hoping to catch nature breaking its own rules. At the same time, these particles act as messengers from otherwise unreachable realms. When a distant galaxy flares in gamma rays, we are seeing processes that happen near its central black hole, in regions we could never visit with a probe. Because gamma rays travel in straight lines and are not easily deflected, they carry a kind of direct line of sight back to their birthplace. In my view, every detection of an ultra-high-energy photon is like receiving a postcard from the brink of some cosmic catastrophe, stamped with conditions of density, field strength and motion that no laboratory can recreate. They let us test how matter behaves in magnetic fields billions of times stronger than anything we can produce, how shocks propagate in plasmas stretching over light years, how particles respond when space-time itself is twisted by rotation and gravity. There is also a softer lesson hidden inside this very harsh light, a lesson about scale and humility. When we first built giant colliders, it was tempting to think of them as final steps toward reaching the fundamental energies of nature. Then the sky informed us, gently but firmly, that particles have been reaching far higher energies for billions of years without any human assistance. Above our heads, in a thin film of atmosphere, cosmic rays and gamma rays are constantly performing experiments for free. Our role is not to dominate that process, but to learn how to read it. For a scientist, that recognition can be both humbling and strangely comforting. We are not the authors of the laws we study. We are the readers of a script the universe has been writing since long before the Earth cooled. From a more personal standpoint, I find that ultra-high-energy gamma rays challenge not just equations, but also narrative. We like stories where causes and effects are tidy, where a single supernova is responsible for a single burst. Yet the more we learn, the more each observed photon seems to be the product of layer upon layer of history. The star that exploded had to form in a particular pocket of a galaxy, shaped by merger events, by earlier generations of stars, by flows of gas stirred up on scales of millions of light years. By the time one gamma ray arrives at our detectors, it carries the imprint of that entire cosmic genealogy, and our task is to disentangle it with just a few flashes of light. In that sense, studying these rays feels very close to philosophy, even to meditation. You are constantly reminded that every moment of observation rests on an ocean of hidden causes. The practical lesson for everyday life may seem distant at first, yet it is there. Ultra-high energy gamma rays show that nature can store and release enormous power in ways that are not obvious from local conditions. A quiet patch of sky can conceal an engine capable of reshaping its galaxy, just as a seemingly ordinary situation in our own lives can hide deep potential or deep risk. They teach patience too. These photons might travel for billions of years before meeting a detector we built in a single human lifetime. Our efforts belong to a much longer story, and that awareness can soften the pressure we place on immediate results. In the end, ultra-high energy gamma rays are not just technical curiosities for specialists. They are part of a broader conversation between humanity and the cosmos. We shine radio waves and laser beams into space. We launch probes, and we build colliders. The universe replies with jets from black holes, with the afterglow of supernovae, with particles that hit our atmosphere carrying energies beyond anything we dared to plan. Each time we catch one of those photons, we are given a chance to refine our theories, to adjust our sense of what is possible, and to remember that the greatest accelerator is not buried underground, but woven into the fabric of space-time itself. And perhaps the quietest, most meditative thought of all is this: somewhere right now, far beyond the edge of our solar system, a single gamma ray is beginning a journey that will outlast civilizations, carrying with it a tiny but precise record of an event we have not yet imagined. Whether we are ready to read that record when it arrives is up to us. What if the gold ring on your finger is really a fossil of a cosmic disaster so violent that it shook the fabric of space-time itself? And what if every atom of platinum in a laboratory and every grain of uranium deep inside Earth's crust began its journey not in a calm nursery of stars, but in a single blinding flash of gamma light on the other side of the galaxy? When we follow the trail of gamma rays, we are not just chasing a strange kind of light. We are tracing the history of the heaviest elements in the universe and asking how something as gentle as a human hand could be built from the wreckage of colliding dead stars. Gamma rays are the most energetic form of light that nature allows. Each photon carries so much energy that ordinary matter barely has time to react before it is pierced and transformed. For a long time, they appeared to us as brief, mysterious flashes on the sky. Sudden spikes in detectors carried on satellites that lit up and then went dark again before anyone could even point a telescope. We called them gamma ray bursts because we had no better name. And at first we did not even know whether they came from our own galaxy or from somewhere far beyond. Gradually, observations revealed that many of these bursts were connected to the deaths of massive stars. But another family of them came from something even stranger. When two neutron stars circle each other, they dance in a death spiral driven by the slow loss of energy through gravitational waves. For millions of years, nothing dramatic happens. The orbit simply tightens, and the stars grow closer, almost like two skaters drawing in their arms as they spin. But in the final seconds, everything changes. The neutron-rich matter of these collapsed stars is ripped apart, heated and thrown into space in a tidal spray of atomic nuclei. The collision releases a flash of gamma rays so intense that for a brief moment it can outshine an entire galaxy. And the debris cloud glows as what we call a kilonova. In that expanding cloud of neutron-rich matter, nature performs an experiment that we cannot reproduce on Earth. The density of free neutrons is so high and the timescale so short that atomic nuclei capture neutrons in a rapid sequence before they can decay. This is the R process, the rapid neutron capture chain that climbs the periodic table step by step until it reaches the domains of gold, platinum, and uranium. In a way, every gamma-ray burst of this kind is like a cosmic forge, a place where the universe mints its rarest coins. It can be hard to feel the scale of this, so let us take a simple example. Imagine a piece of gold jewelry resting quietly on a table. To our eyes, it is just metal shaped by human skill, warm in color, familiar and valuable. But if you could follow its atoms back through time, you would not end up in a calm star like the Sun. You would arrive at a pair of neutron stars spiraling together, each one a city-sized sphere with the mass of the Sun crushed into it. In the final instant of their lives, they tear each other apart, release a burst of gamma rays that could sterilize any nearby world, and throw newly forged heavy nuclei into space. Billions of years later, some of those nuclei become part of a cloud of gas. That cloud collapses into a new star and planets. And one day, a small portion of that debris becomes your ring. Or think of a hospital where doctors use a tiny capsule containing a radioactive isotope of iodine or cobalt to target a tumor. The patient sees only a controlled beam and a machine that hums softly. But the atoms inside that capsule may also trace their ancestry to a kilonova. The energy that once erupted as a gamma ray burst across the cosmos reappears now in a carefully measured dose, serving as a tool of healing. The same physics that once shattered neutron stars now helps a single human life to continue. These connections are not just poetic images. They are the logical consequence of what gamma-ray bursts and kilonovae do to matter. When we model the spectrum of light from these events, we see fingerprints of freshly synthesized heavy elements. When we compare the predicted yields of the R process to the actual abundance of elements in old stars and in the Sun, we find that events like neutron-star mergers can account for much of the gold and other heavy nuclei we observe. In that sense, each gamma-ray burst is not only a violent explosion, it is an answer to a very human question. Where did our material world come from? Understanding gamma-ray bursts also helps us see how these elements spread across the galaxy. A kilonova does not keep its riches to itself. The debris cloud expands at a fraction of the speed of light, mixing with the interstellar medium. Over millions of years, galactic rotation and turbulence smear that material out, so that what began as a localized catastrophe becomes part of the general chemical evolution of the galaxy. New generations of stars inherit a little more gold and uranium than the ones before, and planets forming around them have a richer periodic table to work with. Eventually, on at least one such planet, chemistry gives rise to life. Life develops technology, and technology builds detectors that can finally notice the gamma-ray bursts that made all of this possible. There is a quiet circularity in that story that I find deeply moving. From my perspective as a scientist, the most humbling aspect of this picture is that our theories only reached this level of clarity in recent decades. For much of the 20th century, we did not know whether heavy elements were made mainly in ordinary supernovae or somewhere else. We saw gamma-ray bursts as puzzling flashes without distance or context. It was only when precise localization, gravitational wave detections, and kilonova spectra came together that the pieces of the puzzle began to align. To me, this is a reminder that even the most confident model is only a chapter in a longer conversation between theory and observation. The universe keeps more secrets than we have questions. There is also a personal lesson hidden inside this story of violent light and heavy atoms. We often think of ourselves as separate from the cosmic events we study, as if gamma-ray bursts happened in some distant theater and we were merely spectators. But the truth is quieter and more intimate. The calcium in our bones was born in ancient stars. The iron in our blood once sat in the heart of a supernova, and the trace amounts of heavy elements in our bodies owe their existence to kilonovae and their gamma-ray beacons. When we observe a gamma-ray burst with a satellite, the atoms inside that satellite and the neurons interpreting the data on Earth are made from the products of similar events long ago. The observer and the observed are built from the same cosmic history. This realization can soften the way we think about our place in the universe. On one level, gamma-ray bursts are terrifying phenomena capable in principle of stripping an atmosphere from a planet if they occur too close. On another level, they are part of the chain of events that makes rocky worlds and complex chemistry possible at all. The universe does not separate creation and destruction as neatly as our language does. Often the same process plays both roles at different timescales. From that viewpoint, the right response is not fear but respect. A kind of quiet gratitude that the cosmos is energetic enough and messy enough to produce both kilonovae and contemplative minds capable of understanding them. If there is a guiding message here, it might be this. When we look up and detect a brief flash of gamma rays, we are not witnessing an event unrelated to our own lives. We are seeing a distant cousin of the explosions that shaped the chemistry of Earth and the possibilities of biology. To study these bursts with care, to build instruments that can catch a few stray high-energy photons out of the deep sky, is to participate in a long process by which the universe becomes aware of its own history. In the calm after the calculations and the data analysis, there is a simple thought that returns again and again. The gold in our hands, the fuel in our reactors, and the quiet weight of the world around us are all echoes of gamma light released in moments of unimaginable violence far away and long ago. When we allow that thought to sink in, the connection between human life and cosmic catastrophe stops being frightening and becomes strangely peaceful. We realize that we are not guests in an alien universe. We are one of the ways in which matter shaped by gamma rays and gravity has learned to reflect on its own origin. And in that sense, every time a new gamma ray burst appears on our screens, it is both a mystery to solve and a reminder of something already true within us. That even in the most violent corners of the cosmos, there is room for meaning to emerge. What if every sudden burst of invisible light in the cosmos were not just noise in the darkness, but a message, a map, a kind of cosmic handwriting telling us where the universe is most extreme and most alive? What if every flash of gamma rays was the universe circling a point on the grand chart of existence and whispering to us, "Look here. This is where something extraordinary is happening." When astronomers look at the sky in ordinary light, they see stars and gas and galaxies. A calm and beautiful picture. But when they switch to gamma rays, the canvas changes completely. Suddenly the sky is filled with violent scars, bright pinpricks that flare and vanish, vast regions glowing faintly with the memory of ancient explosions. Gamma rays are the highest energy form of light we know, born where nature pushes matter and radiation to their limits, near collapsing stars, merging neutron stars, feeding black holes, and perhaps even where invisible dark matter collides with itself. By following these elusive photons, scientists are not just measuring brightness or counting events. They are quietly tracing out the skeleton of the most extreme processes in the universe. Imagine you are watching a calm ocean from afar. Its surface looks flat and simple. But somewhere beyond the horizon, a storm is raging. Huge waves crash and whirlwinds rip through the water. You cannot see the storm directly, yet every so often a single towering wave reaches your shore, far higher and stronger than the gentle ripples you are used to. That solitary wave is like a burst of gamma rays, a signal from a storm you cannot see, telling you its location, its power, and even something about the shape of the winds that produced it. In the same way, each flash of gamma light arriving at Earth carries the imprint of the event that created it. And together, these flashes begin to draw a map of the wildest corners of the cosmos. Consider a collision between two neutron stars, each one a city-sized sphere containing more mass than the Sun. Their matter crushed so tightly that a teaspoon would weigh billions of tons. As they spiral together, they twist the fabric of space-time and fling out waves of gravity. Then in the final moment of impact, jets of particles burst out at nearly the speed of light, producing a brief but furious flash of gamma rays that can outshine an entire galaxy. To us, this event appears as a short burst, lasting less than 2 seconds. A sudden spike in the detectors on a satellite. But hidden in that spike is information about the density of the stars, the strength of their magnetic fields, and the precise way they tore themselves apart. That single flash becomes a coordinate on the universe map of extremes, marking the place where heavy elements like gold and platinum were forged and thrown into space. Or picture a massive star reaching the end of its life, its core collapsing under its own gravity, feeding the birth of a newborn black hole at the center, while the outer layers are hurled outward in a supernova. In some cases, narrow beams of incredibly energetic particles punch their way through the dying star and shoot out into space, producing what we call a long, gamma-ray burst. For a few seconds, that single event can release as much energy as the sun would emit over 10 billion years. And if one of those beams happens to point toward Earth, our detectors record it as one of the brightest signals the universe can send. From the timing, the brightness, and the subtle way the light fades, astronomers reconstruct the story of the dying star, turning a handful of photons into a detailed point on the cosmic chart of stellar death and rebirth. Even regions that look dark in visible light can reveal their true nature in gamma rays. The center of our own Milky Way seems like a crowded but ordinary place in optical images, filled with dust and stars. Yet in gamma rays it glows with a strange and persistent brightness, as if something invisible is constantly producing high-energy particles there. Some scientists suspect that populations of spinning neutron stars are responsible. Others wonder if this glow might be a hint of dark matter particles colliding and annihilating each other, converting their mass directly into gamma light. We do not yet know the full answer, but by carefully mapping the pattern of this glow across the sky, comparing its shape with our models of the galaxy, we are slowly sketching the outline of processes that were once completely hidden from view. In this sense, gamma rays function like invisible ink on the page of the universe, revealing structures that no other wavelength can show. For a more human-scale example, imagine living in a city at night and only looking at it through the soft yellow light of street lamps. You would see roads and houses and gentle reflections in windows. Now imagine switching to a view that only shows the brightest headlights of cars racing at high speed, sirens of emergency vehicles, and the flare of industrial furnaces. The city would suddenly appear as a network of motion and danger, with certain intersections blazing with activity while others remain quiet. That second view is what gamma rays give us for the cosmos. Not the calm background, but the urgent highlights where energy flows most intensely. Each detection tells us not only where these hotspots are, but also how the universe transports energy from one scale to another, from subatomic particles to galactic environments. Another subtle way gamma rays act as a map is through the shadows they cast. When high-energy photons travel across vast distances, they can collide with lower-energy light in the intergalactic medium, gradually being absorbed or scattered. By studying how the spectrum of a distant gamma-ray source is softened as it reaches us, astronomers infer how much diffuse light fills the space between galaxies, light emitted by countless stars and galaxies over cosmic history. In other words, the way gamma rays fade with distance allows us to map not only where the most extreme engines are, but also how thick or thin the cosmic fog is along the path. There is also a temporal map hidden within these signals. Some gamma rays were launched billions of years ago, long before Earth even formed. When they arrive today, they carry information about the universe as it was then. Snapshots of ancient explosions that happened when galaxies were still young and the cosmic web was just taking shape. By collecting gamma rays from different distances, we are effectively building a layered timeline of violent events stretching back through cosmic history. each layer adding another contour to our understanding of how the universe grew more structured and complex over time. To make this more intuitive, imagine listening to an orchestra from outside a closed hall. You cannot see the musicians, but through the door you hear the sharp crack of drums, the sudden blare of horns, the swell and fade of strings. From the pattern of sounds you can guess where the percussion sits, where the brass is clustered, even which melodies are leading at any given moment. Gamma rays are like those sharp sounds streaming through the cosmic walls, helping us place the violent instruments in the grand symphony of the universe, even though we cannot walk among them directly. Of course, this mapping is far from complete, and that is part of what makes it so compelling. Every time our satellites detect a gamma-ray burst that defies existing categories, perhaps lasting longer than expected or coming from a galaxy that seems too primitive to host such an event, our map must be redrawn. New lines appear, new regions of parameter space open up, and processes we thought we understood turn out to be only special cases of something broader and stranger. Some bursts appear far brighter than our models allow, as if the jets were narrower or more finely tuned than we thought. Others seem to arise from environments that should not yet exist, according to standard theories of star formation. In this way, gamma rays are not just marking known territory. They are actively pulling the edge of the map outward, forcing us to admit that the land extends beyond where we had drawn the line. On a more contemplative level, there is something quietly moving about the fact that these fierce bursts of light, born in regions utterly hostile to life, can still serve as guides for a small species on a tiny planet. We sit inside the gentle cocoon of our atmosphere, shielded from most of the destructive power of gamma radiation. Yet we build delicate instruments to catch a few surviving photons and decode their stories. In doing so, we turn what could have been pure chaos into information, into understanding, into a way of seeing the universe that would otherwise be forever hidden from us. Each gamma ray that reaches our detectors has traveled across unimaginable distances, dodging clouds of gas, passing between clusters of galaxies, surviving the slow expansion of space itself. By the time it arrives, it is a lone messenger, a single point on our instruments. Yet when combined with millions of others, it outlines patterns we can recognize. Jets around black holes, collision sites of compact stars, echoes of supernovae long faded from view. The universe does not hand us a ready-made atlas of its most extreme events, but through gamma rays it gives us the raw marks from which an atlas can be drawn. In the soft darkness of a control room on Earth, somewhere a scientist watches as a graph suddenly spikes, showing a burst that lasted only a fraction of a second. To most of the world, nothing has changed. The night is the same. The stars look no different. Yet in that small spike is a signpost from a distant corner of the cosmos. A new dot on the map of extremes. Another reminder that beyond the calm light we see with our eyes there is a deeper language of energy and violence, written in gamma rays. And as long as we continue to listen to that language, patiently tracing each burst and glow across the sky, we will go on refining our understanding of where the universe is fiercest, where it forges elements and shapes galaxies, and how all of that distant drama eventually connects back to this quiet world where someone looks up and simply wonders what is happening out there.